What is the role of activation functions in AI? Imagine a neural network as a busy city with countless roads and intersections. Activation functions are like traffic lights that control which cars move forward. They decide if the information from one part of the network should continue on its journey or stay put. Without these traffic lights, the network would just be a straight line, unable to handle complex tasks. When a neuron receives inputs, it first calculates a weighted sum of these inputs. Think of this as adding up all the traffic at an intersection. The activation function then takes this sum and transforms it into an output. This output is what gets passed to the next layer of the network. If the activation function outputs 0 or a small value, it's like a red light stopping the flow. If it outputs a larger value, it's like a green light allowing cars to go. Activation functions introduce nonlinearity into the network. This is essential because real-world problems are often complicated and can't be solved with simple straight lines. For example, recognizing faces or understanding language involves many twists and turns that linear models just can't handle. Activation functions make neural networks flexible enough to learn these complicated patterns. There are several common types of activation functions. The sigmoid function maps inputs to a range between 0 and 1, making it useful for probability tasks. But it can slow down learning because it causes the gradient, or the slope, to become very small. The hyperbolic tangent function maps inputs between -1 and 1, which helps with training but still has some issues with vanishing gradients. The rectified linear unit, or ReLU, is very popular because it outputs 0 for negative inputs and passes positive inputs unchanged. This simple rule helps neural networks learn faster and more effectively. It also reduces the problem of vanishing gradients, allowing the network to train deeper and more complex models. Softmax is another activation function used mainly in the final layer for classifying multiple options. It converts raw scores into probabilities that add up to 1, making it easier to interpret the network's predictions. Choosing the right activation function impacts how quickly and accurately a neural network learns. For example, ReLU is often preferred in deep learning because it supports faster training and better gradient flow. This means models can learn more complex tasks like generating human-like text or creating artistic images. In tools like ChatGPT, DALL-E, and Midjourney, activation functions help these systems understand and generate complex patterns. They are the secret behind how these models can produce coherent language or stunning images from simple prompts. Understanding activation functions also helps in designing better AI systems. It allows developers to build models that are both efficient and reliable. Plus, it provides transparency into how AI processes information internally, which is important for trust and responsible use. To sum up, activation functions are like the decision makers in neural networks. They introduce the nonlinearity needed for AI to learn and perform tasks that are complex and varied. Without them, AI models would be limited to simple, linear problems, missing out on the incredible capabilities we see today.